The next section is eigenvalues and eigenvectors. And I'm going to go back to looking at the covariance matrix I talked about in, I guess it was last Wednesday's lecture. So let's start out with a rectangular matrix R. So it has m rows and n columns. And then I'm going to define R tilde. This is exactly the same R tilde that I had last Wednesday. So remember, we could make this matrix operator that had the effect of subtracting the sample mean from each column of R. So R tilde is just a matrix whose columns each sum up to 0. And then I'm going to take so this is the singular value factorization of this matrix R tilde. And now remember that I could make my covariance matrix. So the covariance matrix for my original matrix R is 1 divided by m minus 1 times R tilde transpose R tilde. And now I have this singular value factorization for R tilde. So generally for homework assignments and anytime you see these, when you have a factorization for a matrix, the very next step is to replace your matrix with its factorization. So I'm going to replace R tilde now with U sigma V transposes. So I end up with my covariance matrix also being equal to 1 divided by m minus 1. And now I have these two singular value, or it's one singular value factorization of the matrix R tilde. And I'm going to use my rules for a transpose of a product of matrices. So I want to take the transpose of this quantity U sigma V transpose. And what I'm going to end up with, so the V transpose gets transposed and ends up in the first spot. So I end up with a V. Sigma gets a transpose, but it's in the middle, so it's just going to stay in the same spot. And then U is going to get transposed and end up in the final spot. And then I'm going to put some, because I'm free to do the matrix multiplications in whatever order I like, I'm going to do this U transpose U first. And since U is an orthogonal matrix, U transpose U is equal to the identity matrix. And so this is just going to go away. And so what I'll end up with is V sigma transpose sigma V transpose. And you have to be a little bit careful here, because if I'd like to just say this is something like sigma squared, but the dimensions aren't correct. So remember, sigma has to have the same dimensions as the original matrix R. So if R is m by n, so it's not a square matrix, then even though you kind of think of a diagonal matrix as having symmetry built in, you can't just say that it's equal to its transpose, because the dimensions won't work, even though the part that doesn't work is all 0. So I have to leave this middle bit as sigma transpose sigma. Oops. But I can look at that and make a little bit more progress. So if I look at sigma, it's diagonal with the singular values down the main diagonal. And now I'm just leaving everything that's 0 blank. So what I mean by this is I'm allowed non-zero values, and they have to be decreasing down the main diagonal. And they have to be decreasing just because that's sort of the convention for singular values. And everything that has I not equal to j is forced to be 0. And then notice the brackets go down a little bit further than the last one, and that's this kind of empty bit down here is just to signify that there's these extra m minus n rows that are all zeros. And then when I take the transpose of this, so the sigma transpose is now just going to have that extra block of all zeros on the right here. But when I start making this product, what's going to happen is I have sigma 1 times sigma 1, and then I'm going to carry on across this row and carry on down this column, and that's just going to be zeros multiplied together. So the 1, 1 element of this. And this is going to end up now sigma transpose is going to be an n by m matrix, so the product will be n by n. And the top left element is going to be sigma 1 squared. And then as I continue doing this multiplication, what's going to happen is if any time I do an off-diagonal multiplication here, whatever singular values on this side is going to hit a 0 over here, and whatever singular values over here is going to hit a 0 over here. So all of the off-diagonal elements of this are going to be 0. And it's only when I hit the diagonal elements, so I do the, say, the second row here times the second column here, I'll have 0 times 0 plus sigma 2 times sigma 2, so sigma 2 squared, and then plus a whole bunch of zeros afterwards. So I'm going to end up with a square matrix, an n by n matrix, that has the squares of these singular values down the diagonal. So sigma transpose sigma is a square matrix with the square of the singular values down the diagonal. Okay, so that's what I just said. And then because they were already positive, we still have this same ordering property. And so now I'm going to define a matrix called lambda to be 1 over m minus 1. So remember from the previous slide, I was carrying this 1 over m minus 1 factor with me, times sigma transpose sigma. And so what I'm going to end up with are the diagonal elements of this matrix are just going to be the squares of the singular values divided by m minus 1. And it's only going to have a non-zero entry wherever this matrix had a non-zero entry, and we just said that that's only going to have non-zero entries down the diagonal. So I'm going to rename this matrix sigma transpose sigma. This is a capital lambda, and then the diagonal elements of my capital lambda, which it's a diagonal matrix, the diagonal elements are going to be called lambda 1, lambda 2, lambda 3, and so on, down to lambda n. And now if I substitute this matrix lambda into my expression for the covariance matrix, so remember I started out with my covariance matrix for my matrix R, and now I'm able to get rid of this 1 over m minus 1 and the sigma transpose sigma, because that's how I've defined lambda. Since this is a scalar value, 1 over m minus 1, I can move it across these matrices to do the multiplication. And so now I have a representation of my covariance matrix for R as V lambda V transpose. So I can write it as an orthogonal matrix times the diagonal matrix times the transpose of the same orthogonal matrix. So this is just something I'm going to need for the rest of this slide and for the next few calculations. So I've used previously the letter E to mean a vector of all ones. When I give it a subscript, so I say E sub j, I mean a vector that's 1 in the jth element and 0 everywhere else. So E1 would be 1, 0, 0, 0 up to the length of the vector. And if you think about what that is just in geometry, if I was talking about a 2 by 2 space, so the vectors of length 2, E1 would be the vector 1, 0, which would just point in the direction of the x-axis. E2 would be 0, 1, which would just be a vector pointing in the direction of the y-axis. So that's what I mean when I say E sub j is a unit vector in the jth coordinate direction. So coordinate 1 would be the x direction, coordinate 2 is the y direction, and so on. And now I want to think about what's going to happen. So I take my covariance matrix, and I multiply it by one of these right singular vectors that are in this matrix V. So it's getting a bit complicated. These are right singular vectors of R tilde, but this is just this one special vector that I like. At this point, it's probably better just to think of them as the columns of this matrix V. So Vj is the jth column of the matrix V. And what's going to happen when I multiply my covariance matrix times Vj? Well, I have this way of writing my covariance matrix down now. So I'm going to replace the covariance matrix by V lambda V transpose times Vj. And now let's think about what's going to happen here. So V transpose has rows V1, V2, V3, and so on. Each one of those is perpendicular to V sub j, except for the jth row, which is exactly the same. So when I do this, I'm going to get zeros everywhere except the jth element, which is going to be Vj transpose times Vj, which is going to be equal to 1. And that's exactly what I said this Ej would be. So this is that sort of first picture I had in the last set of slides, where I'm sort of rotating my system to line up with the coordinate directions. So I have V transpose times V sub j, and that's just going to be E sub j. And now let's think about what happens when I multiply A times a vector V. So this is just going to be one of the ways I could think about matrix multiplication was as a linear combination. So the answer to this matrix multiplication problem is V1 times the first column of A plus V2 times the second column of A, and so on. And now the matrix operation, the multiplication operation I want to look at is lambda times E sub j. And so the E sub j's, that's what's giving me the coefficients here. And all of these are equal to 0 except for the jth one. So all this matrix multiplication is going to do, it's going to give me the jth column of this matrix lambda. So lambda times E sub j is just going to be, so it's 0 times every other column. So it's 1 times the jth column. And then the jth column, it's 0 everywhere up here, 0 everywhere down here. It's only in the jth position that it's non-zero. And the value is lambda sub j. And so I can also write that as just lambda sub j, which is a scalar, times a vector that's equal to 1 only in the jth position. So this lambda, so this matrix times this vector E sub j is equal to lambda times that same vector E sub j, the little lambda, for corresponding to that direction. So this lambda sub j, E sub j. So now I can substitute that. So just to sort of recap where we are, I started out with my covariance matrix times one of these vectors, one of the columns of V, the jth column of V. And I've worked that down to V times lambda times E sub j. But then I can write this matrix lambda times E sub j. That's also equal to just this number times the vector E sub j. So one number is certainly a lot easier to deal with than a whole matrix. So making some progress. And then because that's a scalar, so lambda j is just a number, it's a scalar value, I can bring that out in front. So I can move that across the matrix. And so now the last matrix vector product I have to consider is V times E sub j. And remember, this is just a linear combination of the columns of V, and E sub j is equal to 0 everywhere except for the jth position. So basically what's going to happen when I do this matrix multiplication, I get 0 times the first column of V plus 0 times the second column of V, and then I keep doing that until I finally get 1 times the jth column of V plus 0 times the j plus 1th column of V, and so on up to n. And so the jth column of V is just this vector V sub j again. So what ended up happening, it's all sort of summed up in one line. I have a matrix, some special directions, and when I multiply this matrix, the covariance matrix for R, times one of these special directions, V sub j, I get a vector that points in exactly the same direction, and it's just scaled by a value lambda sub j. So for this special direction V sub j, multiplication by a matrix is equal, it's the same operation as just a scaling operation, as multiplication by a scalar value. So we started out with this v sub j being a right singular vector of r tilde. Define the covariance matrix to be r tilde transpose r tilde. And then by doing that, if we have the right singular vector of this matrix r tilde, when I multiply that by the covariance matrix, it's just going to scale that vector. It's going to stretch it. So I end up with the covariance of r times this vector v sub j points in the same direction as v sub j and is scaled by a factor lambda. So this was a very special case that I just wanted to sort of go through to show where these things are coming from. So in general, so this is only, what I've done here is only for a covariance matrix, so only for this matrix that I can write as the product of r tilde transpose and r tilde. In general, if I have a square matrix, so my covariance matrix was a square matrix. If A is a square matrix, and I want to think about the product A times a vector x, there are going to be certain special directions, x, that are the same direction as A sub x. And these directions are called the eigenvectors of A. So they're the directions that when I multiply by A, I only scale the vector. I don't change the direction it's pointing in. It's not always guaranteed that these things exist. But for covariance matrices, they do. Yeah?
What is the difference between the eigenvector and a singular vector?
So there's two kinds of singular vectors. There's the left and right. And if I make my square matrix by taking r tilde transpose r, then it turns out that the right singular vectors are the eigenvectors of this matrix here, the covariance matrix. But the singular vectors have to be orthogonal, right? Because that was the definition of my singular value decomposition. If I make my square matrix as a product of a transpose of a rectangular matrix times a rectangular matrix, then I end up having orthogonal eigenvectors. But that's not the case in general. So if A is a matrix that I can't write like this, then there's no guarantee that it's going to have eigenvectors or that they would be orthogonal to one another. Is that a good enough answer? Okay. So for these special directions, so the eigenvector directions, the matrix product, so A times an eigenvector, is equal to lambda, so the lambda specific for this direction x times that vector. So there's these special directions where matrix times that direction is just scaling that direction. And the amount of scaling, this lambda sub x, so the scaling for the direction x, the scaling for the direction x is called the eigenvalue. So you have an eigenvector as the direction, and then the eigenvalue is the amount of scaling that occurs in that direction. And so we can use this to do something called diagonalizing a matrix. And I'm able to diagonalize a matrix, so it has to be a square matrix. So I'm going to think of A being n by n now. And if it has n linearly independent eigenvectors, so if there is one eigenvector for sort of each dimension of my matrix, and all of those vectors are linearly independent, then I can put those eigenvectors in a matrix S. So S is a matrix whose columns are the n eigenvectors of A. And then if I pre-multiply A by S inverse and post-multiply A by S, I end up with this matrix lambda that has the eigenvalues down the diagonal. And so the idea here is if I know what the eigenvectors are, I can take a square matrix and I can turn it into a diagonal matrix. So in this case, this is sort of the general idea. S just has to have these eigenvectors in it. For my covariance matrix, we had the extra added property that S inverse, because the eigenvectors were orthogonal, S inverse would be equal to S transpose. So if I have these n linearly independent eigenvectors, I can diagonalize A like this. And then the sort of useful ways of writing this down when you're trying to do calculations with eigenvectors and eigenvalues are you can have A times S is equal to S lambda. It's essentially just the combinations you can get by looking at this and then pre or post multiplying by S or S inverse. I tend to think of this as the most natural one because it's writing it down as a factorization. So I'm factoring A into a matrix of eigenvectors, this diagonal matrix of eigenvalues, and then the inverse of my matrix of eigenvectors. So diagonalization, there's two separate things that you're probably going to get confused later on. So in order to diagonalize, this matrix S has to have an inverse. And S is only going to have an inverse if my original matrix A has n linearly independent eigenvectors. So the requirement for diagonalization is that A has to have n eigenvectors. Later, probably what you're going to want to do at some point is use this in place of an inverse, because the diagonal matrix will be easy to invert, and then we'll know that S has an inverse. But in order to be able to invert, A, so S we know has an inverse because I have an S here and an S inverse here. So we're okay there if I can diagonalize. But lambda, which seem to have changed the size of my slide by accident here. There it goes. Lambda is a diagonal matrix. And I said at the very beginning this diagonal matrix is only going to have an inverse if all of that diagonal elements are non-zero. So invertibility requires that the diagonal elements, none of the diagonal elements of lambda are equal to 0. So there are going to be some matrices that I can diagonalize, but that I won't be able to invert because they'll have one or more 0 eigenvalues. And then the last thing I want to get to is something called the spectral theorem. And so if we go back to my motivating example, motivating example was the singular value decomposition of R tilde and then the covariance matrix for R. So suppose I let A be R tilde transpose R tilde. R tilde is an m by n matrix. Then A is going to be symmetric. And so I think we've already done this exercise. But if you just take the transpose of this, so if I take A transpose, I'll end up with this R transposed times this R transposed transposed. So I get the same thing back. So I can show that A is equal to A transpose. That's the definition of A being symmetric. And the spectral theorem says that every symmetric matrix A, so A being symmetric just means that A is equal to A transpose. So for instance, this covariance matrix I made by taking the product R tilde transpose R tilde, that's a symmetric matrix, has a factorization Q lambda Q transpose. So instead of having this matrix S that just has the eigenvectors in it, I now have a matrix Q that's playing the same role as S, but it's orthogonal. So S inverse just becomes Q transpose because for an orthogonal matrix Q, the inverse is equal to the transpose. So this is a much nicer way of writing this down. I don't have to compute S inverse. If I know what Q is, then I immediately know what Q inverse is because it's just the transpose. And then I can write the factorization into the eigenvectors, so Q, the eigenvectors, and the eigenvalues lambda, like this, with Q inverse equal to Q transpose. And so in particular, what this is saying is if A is symmetric, I get this diagonal matrix lambda that has real eigenvalues in it, and I get this orthogonal matrix Q that also has all real entries in it. And the caveat, so this is just something to be aware of, is if you have a non-symmetric matrix, you can easily end up with, so lambda is my shorthand for eigenvalues, and x is the eigenvectors that are complex numbers. So essentially, there's something kind of going on here that's saying when you have a symmetric matrix like A transpose, it sort of has a square root. Because where do we get complex numbers from? It's when we try to take the square root of a negative number. So somehow matrices that are symmetric, that's something that I can write as a product of, like this, of real valued matrices. If I have a non-symmetric matrix, it's kind of somehow like a negative number. Because if I try to do, if I try to find a matrix like this that's going to give me, a matrix times itself to get A, I need complex numbers to do that. And luckily, a lot of the matrices we look at, so especially in mathematical finance, you're going to be looking at covariance matrices. They are symmetric just because we're going to compute them like this. And so they're going to have real eigenvalues and real eigenvectors. And then suppose the last little thing for this section is concept of positive definite. And so we'll say a symmetric matrix A is positive definite if X transpose AX is greater than 0 for every non-zero vector X. And so this condition, it might seem kind of almost like it's not possible. But if you have a positive definite matrix A, so for instance, a covariance matrix is going to be a positive definite matrix, it doesn't matter what vector. I can put a vector of all negative numbers. I can put mixed vector of negative numbers and positive numbers. But as long as I put X transpose here and X here, when I make this product, it's always going to be greater than 0, except for one special case when X is the 0 vector, and then it'll be exactly equal to 0. And so what you end up with is if I have a symmetric matrix A, so I'm just writing that out as A, B, B, C, so the off-diagonal elements have to be equal to each other. That makes A symmetric. Then when I look at what this matrix product is, so this is X transpose A, X, I end up with AX squared plus, what happened here? So this should be AX1 squared plus 2b times x1, x2 plus c2, x2 squared. And that should always be greater than 0. And the easiest way to see that at least a matrix like this is going to exist is that if I put b equals 0, I have ax squared and cx2 squared. So the x is missing here. And so if I chose A to be greater than 0 and C to be greater than 0, then this product would always be greater than 0. Another way to see that at least one positive definite matrix exists is you could just put the identity matrix here. That would just give you X transpose X, which would be the squared length of the vector. And of course, that's always going to be positive, except for the 0 vector when it would be equal to 0. So we're going to call this form X transpose AX a quadratic form because it represents this quadratic function of x1 and x2. And this is going to have a minimum of 0 at the point 0. And it's going to be positive everywhere else. So this is if A is a positive definite matrix. And so the way to sort of think about what positive definite is suppose I looked at what would a positive definite matrix, a positive definite 1-by-1 matrix be. That would just have to be a positive number. And the way I would think about that is x times a number times x would just be, say, ax squared. And of course, that's going to be positive when a is positive, and it's going to be negative when a is negative. And so a positive definite matrix is just trying to do the same thing, but with a matrix. So a 2-by-2 matrix A is positive definite, is sort of like the same statement of just saying a is a little a here is a positive number. And then I have a R example for what I've done with the eigenvalue decomposition here. And essentially, we just end up getting the same picture that we got when I did the singular values. And hopefully, that's what we should have expected, because we know that this, when I take the, so here I'm taking the eigenvector eigenvalue decomposition of the variance covariance matrix for R. And then I'm just saying S is going to be the eigenvectors, and lambda will be the eigenvalues. And so this square root of lambda 1, this is just the same thing as the first singular value of the matrix R tilde divided by m minus 1, square root of m minus 1, times the first singular vector. And then the second one, the orange direction. So the problem here is that the directions are kind of up to a plus or minus 1. So I end up with a negative 1 times the direction up here. But it's still a vector that's just pointing in the perpendicular direction to the first eigenvector. And they're going to be perpendicular because the variance covariance matrix is symmetric. So I can use the spectral theorem to say that the eigenvalues are going to be an orthogonal matrix.